Exam 2 is going to be covering everything from learning outcomes 1 through 12. So exam 1 covered everything up through learning outcomes 7. Exam 2 will cover an additional 5. That's learning outcomes 8 through 12. Okay, so you've taken quizzes on, you've seen everything from learning outcomes 1 through 10 already on either an exam or a quiz up to this point. Learning outcomes 11 and 12 were covered in sections 4.3 through 4.6. So those ones will show up on the exam. Those will be new. But otherwise, everything else you should be seeing for at least the second time. Okay, some things maybe some things you'll be seeing for the third time, like anything that appeared on a quiz before exam 1. It would have also appeared on exam 1, and now it'll also appear on exam 2, and then exam 3 in the final as well. You'll see it there as well if you haven't gotten it to that point. So remember, just to remind you guys, the structure for this class, you just have to master a learning outcome once, and then once you get it once, then you are done with it for the entire remainder of the semester. You don't have to revisit it again. And so, like, if you've mastered, let's say, like, the first 5 learning outcomes or something, then you'll see learning outcomes 1 through 5 on the exam, but you don't have to do them or anything, right? So you only have to attempt the ones, or you're only, I'll say it like this, you don't have to attempt anything that you have gotten in the past, or you specifically shouldn't. There's no benefit to redoing problems that you've already gotten right. Okay, so if you've, say, gotten, like, let's just say that you've gotten, like, 2 learning outcomes, the first 2, then since there's going to be 12 on this exam, that leaves 10 that are left to attempt. Now, does that mean that you have to do all 10 remaining problems that you haven't gotten yet? No, of course not. It would be pretty unrealistic for me to expect you to get 10 problems totally right on an exam. So that is not at all my expectation. You should basically come in with an idea of which learning outcomes you are planning to attempt, and then spend a lot of time studying those ones. And then maybe don't spend as much time on the ones that you aren't particularly planning on attempting on the exam, right? So what you don't want to do, what's going to sort of set you up for failure, would be if you have, say, gotten 0, 1, or 2 learning outcomes completed up to this point, and then you come into the exam just being like, I'm just going to knock everything out, and then you study everything, and then you plan to get everything, but when you study that many different concepts all at once, you're just bound to kind of have some gaps in your knowledge. You're probably going to go in being maybe 80% sure how to do something on problem 1, and maybe 70% sure for problem 2, maybe 50% sure for problem 3, 90 for 4, 70 for 5, whatever. The point is, if you don't have a close to 100% understanding of a learning outcome, you're probably not going to demonstrate mastery on it, right? The standard for mastering a problem, you have to get it completely right. So you have to really understand what's going on in that problem. So I don't want you to come into the exam with a 50% understanding of something, or even an 80 or 90% understanding of something. I would rather you come into the exam with a 100% understanding of 2 or 3 concepts than a 80% understanding of all of the concepts, because 100% understanding of 2 or 3 concepts is going to get you 2 or 3 problems right, and a 80% understanding of all of the concepts is going to get you a 0 on the exam. And I would rather see you come away with a couple of points than 0 points, right? I am hoping that everyone does as well as with this as they possibly can, right? That there's nothing in it for me to see any of my students fail. It's strictly the opposite. I want to see, and I will benefit from a personal and professional standpoint, I will benefit from seeing as many of you succeed as possible. So I really, really do want to see that. So please prioritize your studying effectively. Right. Now, just for perspective, there is a pretty wide range of outcomes of like, how many problems students have gotten up to this point. There are students, so you've seen problems on the first 10 learning outcomes. There are several students who have gotten 0 learning outcomes completed so far, and there's a few, not that many, but a few that have gotten all 10 of the ones that you've seen so far mastered, right? And so, and then there's pretty much everything in between. So the scores are kind of like, we're not even halfway through. We haven't seen like half of the exams yet. Exam 2 will mark the halfway point for the exams that you'll see in the course, because there's 2 exams. There's 3 exams and a final, so 4 exams. And so, what am I trying to say? Basically, I want you to sort of just kind of go in understanding everyone's kind of pacing themselves their own way. And you need to think to yourself, how do you need to pace yourself in order to get the grade that you are going for? Now you can see over here the grade breakdown. I'll just go over this one more time before I jump into the material. Feel free to skip ahead to the material if you want. But if you're trying to just pass the course, so the learning outcomes make up 75% of your grade. And then the projects make up 10%, and WebAssign makes up 15%. Maybe those are reversed. I think that's the correct order, but regardless, those two make up 25% of your grade, and the LOs make up 75%. So if you are going for a passing grade, you need a 73%, or a 72.5, or round up or something like that. And so the minimum number of learning outcomes that you need to get there, I believe, would be a 9. Because if you get 9, that would be 64 out of 100 points. And if that is making up 75% of your grade, that I believe would be equal to 48%. And so if you get, if you have a 0% on the projects and WebAssign, then your final grade for the class is a 48%. And if you get a 10 and a 15%, so basically get all of the project points and all of the WebAssign points, that's your final grade is going to be that plus the remaining 25%, which is 73%, which is passing, okay? And so you can kind of figure this out based off of this chart and what grade that you want. Just assume that you're getting like if you want to get, if you're on pace for like a 21% from the projects and WebAssign, then you would probably want to get like 1 more learning outcome in order to pass, so 10 learning outcomes. If you're on pace for a 25% and you're just shooting for an A in the course, then you can kind of do this similar computation to see how many of these learning outcomes you need to get in order to get an A, which would be like a 93%. It would probably be somewhere in like the 15 to 18 range, right? Maybe if you got a 16, that would give you a 90% for your learning outcomes grade. Certainly that would probably put you in an A range. I think probably a 15 would also give you an A. Let me just do the computation real quick. Please don't give me ads. Please load. Never seen a calculator take this long to load. All right, there we go. Ads, great. So if you do 88% of 75, that's 66, plus the remaining 25. That puts you at a 91. And so that's a little bit below learning outcomes grade, which corresponds to 15 learning outcomes. That puts you at an A minus. 16 and above puts you at an A for the class. All right. So let's jump in. So I already spent a bunch of time on a different video talking about learning outcomes 1 through 7. I'm not going to do that again. I'm going to focus on learning outcomes 8 through 12 and the specifics of sort of what you need to know about these each of these learning outcomes. So learning outcome 8 is on modeling using differential equations. This is covered in 3.1 through 3.2. So you need to do a couple of things here. So you need to know how to set up differential equations and initial value problems corresponding to given real-world situations, including exponential growth and decay models, logistic models, Newton's law of cooling, and mixing problems. All right, and then you need to be able to solve these problems using Chapter 2 techniques. All right. So for example, if you had something that was like an exponential growth model, you would need to set up a differential equation for that exponential growth model. So that's usually saying something like the rate of change of population is proportional to the population present. So the differential equation that goes along with that would be dp dt equals k times p, because it's saying that the rate of change of population is proportional to the population present, which is p. So that's your differential equation. And then if it tells you that like your initial population is like 100, then that tells you that the population at time t equals 0 is equal to 100. So p of 0 equals 100. Now all of a sudden this is an initial value problem. This would usually not be enough to specify a unique solution because you need to know what that value of k is. So it would probably also tell you something like p of 5 is equal to 200, or maybe it would tell you equivalently that the doubling time of this population is 5 years, because it takes 5 years for the population to double from 100 to 200, right? So it could give you some information like that. And so this would be something that you should be able to solve. This you would solve using separation of variables, because you can just separate the variables and then just integrate. You get ln of p equals kt plus c, and then you can solve for p. You end up getting like c e to the kt if you do all that stuff, etc. Newton's law of cooling, that's the one where it says that the so T is like your temperature, little t is time, temperature of like some object. Then it would tell you that the rate of change of the temperature is proportional to the difference between the temperature of the object and the temperature of its surroundings. So you might write T sub S as a placeholder for that, or if you know that like the temperature of their surroundings is like 70 degrees Fahrenheit or something, like if the room temperature is 70 degrees, then you do T minus 70 for that. All right, this is also separable, so you would solve it in like the same sort of way. It would probably give you some information like the initial temperature of the object is 100 degrees, like when it gets like taken out of an oven or something like that, and maybe 5 minutes later, if T is in minutes, then the temperature might be 90 degrees, something like that. So you could solve it in those sorts of ways and see, you could ask further things like how long does it take for the temperature to reach 80 degrees and so on and so forth. Logistic model, I probably wouldn't ask you to solve the logistic model because it kind of is pretty tedious, but I would ask you like what the differential equation modeling the logistic model is. That would be dp dt equals kp times m minus p. So it's really similar to the regular population model, dp dt equals k times p, but it's also proportional to the difference between the maximum population and the population present. So here it's proportional to the population present and m minus p, which is the number, the difference between the maximum and the present population. Okay, so m is like your carrying capacity here, or like your maximum population. And then let's see, Newton's law of cooling, just covered that. Mixing problems, there's not like a standard differential equation to go with that, but those are the ones that kind of have, so you have some mixture, so maybe you have like some water, maybe you have like 100 gallons of water at t equals 0, and maybe it's like 5 pounds of salt at t equals 0, and it tells you that it's pumping in 3, or let's say it's pumping in a brine with 3 pounds of salt per gallon at a rate of 5 gallons per minute. And it mixes everything and pumps out at a rate of, say, let's say 8 gallons per minute. Okay, so I won't go through like solving this, but you can say that like if A is the number of, or the amount of salt at time t, then the rate of change of the salt is going to be R in minus R out. So the rate at which salt is being pumped into the tank minus the rate at which salt is being pumped out of the tank. So the rate at which salt is being pumped into the tank, so you're pumping in 3 pounds per gallon at a rate of 5 gallons per minute. So it's going to be 15 pounds per minute. And the rate at which salt is being pumped out of the tank, it's going to be, well, some number of pounds of salt divided by how many gallons, but it's being pumped out at a rate of 8 gallons per minute, right? So you don't know necessarily how many pounds of salt there are and how many gallons there are at time t, but we can figure that out. Well, how many pounds of salt are there at time t? There would be A pounds of salt at time t. That's literally what A is, the amount of pounds of salt at time t. That's just how we define the variable. And how many gallons of water they're going to be? Well, there starts off with 100, but that's at time t equals 0, right? We're pumping in 5 gallons of liquid each minute, and we're pumping out 8 gallons of liquid each minute, right? So 5 gallons in, 8 gallons out. After 1 minute, it's going to go down by 3, right? And after t minutes, it's going to go down by 3 per minute. So 100 minus 3t is how many gallons of liquid there are at time t, right? And so this would be the rate at which salt is being pumped out of the tank. So this is 8a over 100 minus 3t, something like that. And so dA dt would just be 15 minus 8a over 100 minus 3t. So that's your differential equation, right? This turns out to be linear, and so you can solve this using an integrating factor method. That's chapter 2 stuff, so I'll just kind of move forward from there. Okay, LO9 is on second order differential equations. This is sort of the overview section. This is covering 4.1. So you should be able to determine whether a set is a fundamental set for a homogeneous differential equation. And then you should be able to identify a particular solution for simple, basic, non-homogeneous DEs, and then give the general solution. So these are the ones where I basically tell you what the fundamental set is, and you have to verify it. And then if the differential equation is like simple enough, you should be able to find a particular solution and then use all that information to just put everything together. So this might be something like, I might tell you to verify that e to the x, let's say like e to the 2x, and then x e to the 2x is a fundamental set for y double prime, let's see, minus 4y prime plus 4y equals 0. And so you need to do two things to check that. The first thing that you need to do to check that is actually plug your y1 and y2 into the differential equation. So y1 is e to the 2x, the derivative is 2e to the 2x, the second derivative is 4e to the 2x. Plug that stuff in to that differential equation, and you get 4e to the 2x minus 4 times 2e to the 2x, that's our y prime, and then plus 4 times y, which is e to the 2x. This is equal to 4e to the 2x minus 8e to the 2x plus 4e to the 2x. 4 minus 8 plus 4 is 0, so this is equal to 0e to the 2x, or just 0. That's the right-hand side. This is your left-hand side. So the left-hand side and the right-hand side are equal when you plug it into the differential equation. So y1 satisfies the differential equation. You should do that for y2 as well. So that's x e to the 2x, y2 prime. That'd be, do a product rule. You get this, and then another derivative. You get 2e to the 2x plus, do a product rule in that term. You get 2e to the 2x plus 4x e to the 2x. Just doing it like that. So that would be 4e to the 2x plus 4x e to the 2x. Plug in, show that the left-hand sides are equal, so on and so forth. I'll spare you the details. And then, sorry, we're not on B yet. I should have labeled these differently. So that's like thing number 1 that you have to do for part A. So this is all like a part A kind of thing. And then the second thing you would have to do for part A would be show linear independence. To have a fundamental set means that 1, everything in there is a solution, and 2, the set is linearly independent. Okay, so we want to show that this is a linearly independent set, and the way that you do that is by computing the Wronskian. So the Wronskian is the determinant of the matrix that you get when you put y1 and y2 in the first row, and then their derivatives in the second row. Like so. And then you want to compute this determinant and then show by simplifying that it's not equal to 0. So if I multiply all this out, we'll get e to the 2x times e to the 2x plus 2x e to the 2x minus the cross terms here. So that would be 2 e to the 2x times x e to the 2x. Remember that the determinant of matrix is going to be this times this minus this times this, right? AD minus BC. All right, now we need to simplify this and show it is non-zero. So we'll distribute this e to the 2x everywhere. So e to the 2x times e to the 2x is equal to e to the 4x, and then plus 2x times e to the 4x. And then minus, this will be 2x e to the 4x. Remember that if you do like e to the a times e to the b, that the exponents add, so you get a plus b, something like this. And so if I do 2x e to the 2x times e to the 2x, that would be e to the 2x plus 2x, which is 4x. And so these two terms cancel, we get e to the 4x, and e to any power is always non-zero. Yeah, I don't think we need to explain that. So e to any power is always positive. You could just say always positive. I think that gets the point across. Yeah, so it's linearly independent. Great. All right, so that's like what your part A would look like. Part B would be identifying a particular solution. So if you have something like, so this is a homogeneous DE. So if I want to take a non-homogeneous DE associated to it, maybe say that this is equal to like 8 or something, or let's say 16. Whatever, it doesn't matter. So for something like this, if your right-hand side is like a constant function, or if it's like a linear function, then you can just assume that your particular solution is also linear or also constant. So here you can assume that it's constant, and then y prime is equal to 0 and y double prime is equal to 0. And so plugging that stuff in, you get 0 minus 4 times 0 plus 4 times y is equal to 16. So then y dividing everything by 4 would be equal to 16 over 4, which is just 4. Okay, so that would be your particular solution. And then your general solution, let me move this down a little bit. And then your general solution is your particular plus complementary. And so that would be 4 plus whatever our complementary solution is. And our work from part 1 basically tells us what the complementary solution is, because if we know that y1 and y2 form a fundamental set, then our complementary solution is going to be c1y1 plus c2y2. So we'll get c1 e to the 2x plus c2 times x e to the 2x. So that's our general solution. Okay. All right, for reduction of order, so I'm basically just going to give you the formula for this, and this, in my opinion, is one of the easier ones to get, because it's kind of just, you need to know what the formula is used for, what the point of it, and you need to actually be able to, plug everything into the formula, try to get a little bit of practice with this, because there's kind of it's like integrals inside of integrals. Is very much like an algebra, just calculus sort of problem of just kind of doing the computations. As long as you can do the computation and know what it's used for, you should be okay on this. But so reduction of order formula, the context is you start with a solution y1 for a homogeneous DE, and then your other solution y2 is going to have the form y1 times e to the negative p of x dx divided by y1 squared, and then integrate that whole thing with respect to x. So if you know that like y1 equals x is a solution for something like, let me say, I want to say something that's correct. All right, so let's say that y1 equals 5 is a solution for y double prime plus like 2 over x y prime equals 0. So this is homogeneous. All right, it's homogeneous because the right-hand side is 0. And you can tell that this is actually going to be a solution because if you plug a constant function in, y prime is going to equal 0, y double prime is going to equal 0. So of course, plug in 5, you're just going to get 0 out. Here, your p of x is equal to 2 over x. If there was like a negative there, then it would be negative 2 over x, right? And so y2 would equal y1, which is 5, times the integral of e to the negative p of x, which is 2 over x dx, all over y1 squared dx. And so you just kind of go through this whole computation. So you want to integrate this 2 over x thing first. So this is e to the negative 2 ln of x. That's just over 25. You could bring out that 25, so 5 over 25. And this is e to the ln of x to the negative 2. So that's 1 over 5 times, so e to the ln of something is just x to the negative 2. You could drop the absolute values because that exponent is even, which makes it positive. And so then you can just integrate. So this is 1 over 5 times x to the negative 1 over negative 1, or just negative 1/5 x to the negative 1. So that's your y2. And then move this down now. And then your general solution is going to be y equals c1 times y1, which is 5, and then plus c2 times y2, which is negative 1/5 x to the negative 1. Okay, solving second order differential equations. You need to be able to find the complementary solution for a non-homogeneous dE using the characteristic equation. You need to be able to find a particular solution for a non-homogeneous dE using the undetermined coefficients approach. And you need to just give the general solution for the non-homogeneous dE. Finding the complementary solution, this is all like the stuff in like 4.3. So this is basically just solving things where the right-hand side is equal to 0. I know non-homogeneous means the right-hand side is equal to 0, but the complementary solution is when you take that non-homogeneous thing and make it homogeneous, right? So the complementary solution for, say, y double prime minus 2y prime plus y equals 5x, the complementary solution is the general solution to that same differential equation, but with a 0 on the right-hand side. And to solve this thing, you want to convert that to your characteristic equation, which is a polynomial, and then you want to try to either factor that polynomial. This factor is as lambda minus squared in this case. And so your roots would just be 1 with that's a repeated root, so it's multiplicity 2. Or maybe you can get like 2 complex roots, or maybe you get 2 distinct real roots, like multiplicity 1 for both of them, right? So if it factors as lambda minus 1 squared, then your solutions would be e to the x and x e to the x. Those would be, or that would be your fundamental set rather. So your general solution would be c1 e to the x plus c2 x e to the x. If you had something that factored as lambda minus 2, lambda minus 3, then you would get y equals c1 e to the 2x plus c2 e to the 3x. Right. And so yeah, that's that. And then if you had something that maybe it doesn't factor, maybe you have like lambda squared plus 4 lambda plus 13. If you can't factor that, then you'll have to go to the quadratic equation. So you get lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's negative 4 plus or minus 16 minus 52 over 2 plus or minus, so that's negative 36. Whenever you have the square root of a negative number, you could just take whatever the square root of that number is. Square root of 36 is 6, and then square root of negative 36 will just be 6i, right? Because the square root of negative 1 is literally just defined to be I. This is all over 2, so you can just cancel the 2's with everything. You get negative 2 plus or minus 3i. All right, and so if you get something like this, then your solutions would be e to the negative 2x times cosine of 3x and e to the negative 2x sine of 3x. Right? So those would be your y1 and your y2, and so your general solution would be c1 y1 plus c2 y2. So that's how you solve the homogeneous things. That's how you find the complementary solutions for stuff. And then for the what do you call it, non-homogeneous stuff. So if you have like a right-hand side, let's say like y double prime plus y equals like 4x squared plus 3x, something like this. This is when you do like the guess and check method, where you say like, all right, well, y sub p is going to be, so this is a quadratic. So you're going to say y sub p is also quadratic. So ax squared plus bx plus c. Note that over here, the plus c is really like a plus 0. So you do need to have the plus c in here. Otherwise, it's just not going to, it's probably not going to work. It technically might, but include the plus c to account for more possibilities. And then you'll, compute the derivatives, 2ax plus b, and then 2a. Plug all the, all of these things into your left-hand side. Set all your x squared coefficients equal to the x squared coefficient on the right, which would be 4. Set all your x coefficients equal to the x coefficient of 3 on the right. And then combine all of your constants on the left, set them equal to the constant on the right, which is 0 in this case. Right? Where it gets more complicated is when your, let's see, maybe your right-hand side is something like x e to the x or something. So if you have x e to the x, then if, how do I say? Yeah, so if you have x e to the x on the right-hand side, then you're also going to want to include, all right, so this would be, I'll say it like this. So this would be like your initial guess, right? Now, if you compute the derivative of your initial guess, you'll get some e to the x terms in there. And so because this like e to the x term is like showing up over here, you're also going to want to include some e to the x terms in your initial guess. So you want to modify this initial guess by including some e to the x term up in there, right? And so I have this plus b e to the x, and then compute y double prime. That would be a e to the x plus another a e to the x plus ax e to the x, doing a product rule on that guy. And then plus another b e to the x. Plug all that stuff in, set it equal to your right-hand side. So this should give you enough like degrees of freedom to be able to actually solve for a and b. And then the last thing you need to kind of look out for is, let's see, let's say that your fundamental set is something like sine of x cosine x. Let's say that that's your fundamental set for your complementary solution. So your complementary solution might be like c1 sine of x plus c2 cosine of x. And then let's say that you have y double prime plus y equals sine of x on the right-hand side. So you might guess initially, like, all right, well, let's do a sine of x for our particular solution. All right, well, this isn't actually going to work out even for like, even disregarding your complementary solution, because you're also going to need, a b cosine of x term over here, because cosine appears as the derivative of sine, right? So this should really be your initial guess, because you have a sine of x term on the right. Your initial guess should be a sine of x plus b cosine of x. All right, and then this is where the complementary solution comes in. Both of these terms appear in the complementary solution. So to fix this guess, what we'll do is multiply any terms that get duplicated in our complementary solution, multiply them by x. So you do ax sine of x plus bx cosine of x. So just multiply both of those terms by x because they're both showing up in your complementary solution. And so if you do this, I mean, I probably wouldn't do this one specifically on an exam because you just have to keep doing like a bunch of product rules. So this would be like a sine x plus a x cosine x, and then plus b cosine x plus, or I guess that'd be minus b x sine of x, right? And then you have to do like a couple more product rules. Sorry, that was yp prime and then yp double prime. You have to do some more product rules on that, and then you plug everything into y double prime plus y equals sine x. So maybe this one specifically I wouldn't do, but maybe something with like an e to the x term shows up in your complementary solution, and you have an e to the x on the right hand side, then you might need to multiply your initial guess by making it like x e to the x, or maybe x squared e to the x, or something like that. All right, so a bunch of examples in the notes and in the textbook to get a little bit more practice with that. This is like one of the sections that has kind of the widest variety of problems that you could kind of see. So this one probably more than most of the other ones, maybe except for, what was it, learning outcome 8. So learning outcome 8 and learning outcome 11, in my opinion, have like the widest range of possible questions that I could ask, because there's like just kind of a big variety of types of questions that you might see on there. Like with learning outcome 8, there's a bunch of different differential equations that you should know how to model and stuff. And with outcome 11, based off of how the right hand side for your non-homogeneous thing looks like, based off what your complementary solution looks like, again, there's just kind of a big variety of like things that you can kind of see in there. So I do recommend doing as many of those practice problems as you possibly can. So if you go to, is it in here? Let's see, this is section like 4.4. Yeah, so like if you do like, so go into the textbook, like section 4.4, just pick like any of the problems from like 1 through 26. Like any of them are fine, just to get some like extra practice. 4.3 has some listed as well. So here's some practice problems from section 4.3 that you could do. 4.4 tends to cover a lot of the stuff from 4.3. Yeah, you kind of need to know 4.3 in order to do 4.4. All right, and then variation of parameters is the last thing. So again, you need to know how to find the complementary solution. So we already went over that, but you need to know how to do that here as well. And then part B, you need to be able to find a particular solution for a non-homogeneous DE using variation of parameters. So this is where you do the whole u1 equals the integral of w1 over w, and u2 equals the integral of w2 over w. And then y sub p is going to be u1 y1 plus u2 y2. All right, so that's the setup for it, right? The whole setup is basically you start with a y1 and y2. Either that y1, y2 complementary solution or fundamental set will be handed to you, or you might have to find it by factoring the characteristic equation or something like that, using quadratic equation or whatever. So you need to find your y1, y2 in most situations. And then you'll compute the Wronskian based off of that, put y1, y2 at the top, and then compute the derivatives for the second row, and then compute that and simplify. W1 is going to be replace your first row with first column with your whatever your answer column is, and then W2, and then of course you'll want to simplify this as well. W2 is replace column 2 with your answer column, then simplify. And then you're just going to want to put W1 over W into an integral. So you're always going to want to simplify these integrals as much as you possibly can. And like U2 is going to be the integral of W2 over W. And then once you integrate those things, as long as you integrate them correctly, then your particular solution will just be u1, y1 plus u2, y2, where your y1 and y2 are just coming from your fundamental set. Okay. Yeah, so that's variation of parameters in a nutshell. Again, I recommend going through the 4.6 notes, just making sure you can do all the problems in there. Like for example, we didn't have time in class for finishing like example 3 or example 2 in like a lot of detail. Like I gave you guys like the last like 5 or 10 minutes of class to work on example 2, and then just kind of like just showed you like what the answer kind of looked like, and then for example 3 I just kind of like posted the solutions online. But yeah, let's look at example 3 actually, just because we can. So if you wanted to solve y double prime minus 2y prime plus y equals 6 e to the x plus 4 using variation of parameters. All right, so this is actually one that you could solve just fine using the techniques from 4.4, like the guess and check thing, because you could just say like yp equals a e to the x plus b, and then you should be able to just plug that in, like plug that and then y prime and y double prime into your equation and solve for a and b. That would actually work out just fine. But if you want to, just get a little bit of practice with variation parameters, this is what it would look like. So W would just be, the first thing you would do is get your characteristic equation, factor it. Factors is lambda minus 1 squared. So your y1 is e to the x, your y2 is x e to the x. And so your Wronskian, you just put your y1, y2 at the top, and then compute the derivatives for the bottom. You have to do a product rule in this one. And then your answer column would be 0 and then whatever's on the right-hand side, assuming that you normalize. So you always have to normalize these guys. This guy has been normalized for you. But if there was like a 2 in front of the y double prime, you would have to divide everything by 2. And then after dividing by 2, then you'll put whatever's on the right side for your answer column. All right, so anyway, W1 is replace old column 1 with your answer column, and W2 is replace your old column 2 with your answer column. Right? W1, that derivative would be 0 minus x e to the x times 6 e to the x plus 4, which simplifies as this. W2 would just be e to the x times 6 e to the x minus e to the x times 0. That simplifies as this. Right? And then your Wronskian should simplify as just e to the 2x, because you do e to the x times that guy minus e to the x times x e to the x. And so these x e to the 2x's will just drop off, and you're left with an e to the 2x. I remember that e to the x times e to the x is equal to e to the 2x. That's where the 2 is coming from. So what's your u1? It's going to be the integral of w1 over w. And so your w1 is equal to this, and your w is equal to this. So you just divide these out. You want to simplify as much as you can before you actually do anything. So you can cancel out an e to the 2x over there, and cancel out e to the x over e to the 2x simplifies as e to the negative x over there. So this simplifies to negative 6x minus 4x e to the negative x. You can integrate negative 6x as just negative 3x squared. And then this like 4x e to the negative x thing over here, you could just do an integration by parts thing. So set u equal to negative 4x and dv equal to e to the negative x, and then do integration by parts, and you should be able to integrate it just fine. U2 would be the integral of w2 over w, which when you simplify this would just be 6 plus 4e to the negative x, which simplifies as 6x minus 4e to the negative x. After you integrate that, so that's your u2, this was your u1, and so your general solution is going to be, well, your complementary solution plus your particular solution. So complementary is just going to be c1y1 plus c2y2, and then your particular is going to be u1y1 plus u2y2, right? So our y1 and y2 are e to the x and x e to the x, right? So C1Y1 plus C2Y2. And then for our particular, we get U1Y1 plus U2Y2, where this is our U1 that we computed, and this is our U2 that we computed. You could probably simplify this quite a bit. I just opted not to. You don't have to on an exam. If you just left it like this and left it unsimplified, that's fine by me. It's probably easier for me to grade it that way anyway. So if you choose to simplify it, that's your choice. I don't really care. It's up to you. All right, so that's probably enough from me. Hopefully this helped. There's some other videos from previous semesters going over like those old exams, which of course the format for those old exams is different. This is the first semester I'm doing mastery grading with differential equations, and so obviously our exam format is different, but hopefully you can still look at those problems and take away the general concepts from what was going on with those. So let me know if you have any questions. Hope this helped, and see you guys shortly.